Hello everyone, it's lecture 16 and Algebra by Itorrent Academy, and we have here eigenvalues and eigenvector. If I have this matrix A equal to here 1, 2, negative 1, here 4, okay, and here we have vector x column vector with here 2 and 1 and ask it to multiply matrix A into vector x. So we have here A x will be equal to here we have 1, 2, negative 1, 4 and 2 x to 1. This will be the vector of here. We have to multiply first row into this column and again second row into this column of vector x. So we have here 1 into 2 equal to 2 plus 2 into 1 equal to 2. So we have here 2 plus 2 and here we have negative 2 plus 4. So this will be equal to here 4, 2, and I can say that this will be equal to here I will take 2 as a common. So we have here again 2 and 1. Okay, so I can say that if I want to make change to this vector x by multiply it by this system matrix A, okay, I can replace a scalar value to okay, so easily I can replace system matrix A by scalar value 2, okay, so let me write that here we have A into vector x will be equal to 2 scalar value into here vector x. So I can say that 2 here is the eigenvalue of matrix A, okay, and here x is eigenvector of matrix A, okay, and to generalize that, so we can write this as Ax will be equal to lambda, which refers to the eigenvalue into x. Okay, so we have here a x minus lambda x equal to 0. We can take x as a common, so we have here and focus on this minus here we have x, and but I can subtract scalar value from matrix, so we have to multiply the scalar value into identity matrix. So we have here lambda I. Okay, so this value of lambda only related to matrix A. So I can call lambda the eigenvalue proper or characteristic of matrix A, okay, which can represent matrix A in the operation of in the operation on vectors. Okay, so let me clear and start to sense this with an example. First example asks to find the eigenvalues and eigenvectors of the matrix A equal to -5 to 2, okay, so first of all, a matrix A with dimension n into n has n number of eigenvalues, okay, and for steps of our solution, here the first step to use characteristic equation to get eigenvalues. Okay, here we have from this equation a a minus lambda I into x equal to 0. This is a homogeneous system, and here we have two ways. We have a trivial solution, unique solution if the characteristic equation a minus lambda I doesn't equal to 0, and we have here infinite solution if a minus lambda I here equal to 0. Okay, so here we have to get the determinant of this matrix A minus lambda I and put it equal to 0, okay, to get values of lambda. Okay, again with the next step is to use here Gauss Jordan method to find eigenvalues. vectors. Okay, we have here to solve the system of equation here of a minus lambda I into x equal to 0 to find here eigenvectors x. Okay, let me just here the first step is to use characteristic equation. So let me find here first step is to make determinant of a minus lambda I equal to 0. So let me find a minus lambda I here. A minus lambda I will be equal to, here we have a negative 5 to negative 2 minus here identity matrix into scalar value lambda. So we have here lambda and the diagonal, and here 0 0, here lambda multiplied by 1, here lambda multiplied by 1. So this will lead us to negative 5 minus lambda to negative 2 minus lambda. Okay, so here we have to get the determinant of this matrix. We have here negative 5 minus lambda to negative 2 minus lambda. So this will be equal to the product of principal element and principal diagonal minus product of element and secondary diagonal. So we have here negative 5 minus lambda into negative 2 minus lambda here minus 2 into 2 here 4. Okay, so just we have here 10 here plus 7 lambda. Okay, here plus lambda square minus 4 equal to 0. So lambda square plus 7 lambda plus 6 equal to 0. So just to factorize this equation, we have here lambda plus 1, lambda plus 6. So lambda equal to negative 1 and lambda equal to negative 6. And I can write set of eigenvalues as this. We have here row of A will be equal to set of values of eigenvalues of matrix A. So we have here negative 1 and here negative 6 and row here called spectrum A, and here the largest absolute value of eigenvalues. Here we have equal to 6. This called spectral radius. Okay, so thus we have here lambda equal to negative 1 and lambda equal to negative 6. Okay, so just here move to step 2. We have to solve this system of here a minus lambda I into vector x equal to 0 using Gauss Jordan. Okay, so we have this system. First f lambda equal to negative 1. So we have here a this matrix. So here negative 5 minus negative 1. So we have here negative 4. Here 2. 2. Here negative 2 minus negative 1. So here we have negative 1. Okay, and 2 here x1 x2, the elements of vector x equal to 0. Augment this matrix to the free term here. So here we have by using Gauss Jordan. So we have here negative 4, 2, 0, 2, negative 1, 0. Okay, make row operation of first here divide by first row by negative 4 to make the first element equal to 1, and here multiply first row by negative 2, then add to second row. Okay, so this will be equal to here 0, 0, here 1, negative 1 half, and here multiplied by negative 2, then add to 2, we have here 0, multiplied by negative 2, then add to negative 1, so we have here 0. Okay, so from here we have x1 minus 1 half x2 equal to 0, and equation equation in two variables. Okay, so just we can let x2 equal to 2 alpha, and alpha here is an arbitrary number, alpha arbitrary, number. Okay, so then x1 will be equal to here 1 half x2. So x1 will equal to alpha. Okay, so I can write my eigenvector here. X1, x2 will be equal to here alpha 2 alpha, which equal to alpha and 2 1 2. Okay, so here the first eigenvector is 1 2. Okay, again if here x again with lambda equal to negative 6. So we have here this system here negative 5 minus negative 6. We have here 1 2 2, and here we have 4 and 2 x1 x2 equal to, let me write this as a vector. So we have here 0 0 using Gauss Jordan. So here we have 0 0 1 2 2 4. Row operation here is to multiply first row by negative 2, then add to second row. So here this will be equal to 0 0 1 2. Here we have multiplied 1 by negative 2, then add to 2, so we have 0. Multiply 2 by negative 2, then add to 4, so we have here 0. Okay, so here from here x1 plus 2x2 will be equal to 0. Okay, so here we have, so let x2 equal to negative alpha, then x1 will be equal to 2 alpha. So I can write my vector x1 x2 equal to here 2 alpha, here negative alpha. So we have here alpha as a common, and here we have 2 negative 1. Okay, so just in 2 steps we can get the values of eigenvalues and eigenvector. So again, our solution here from the first step, we get lambda equal to negative 1, lambda equal to negative 6, all the spectrum of A equal to set of negative 1 and here negative 6. From the second step, we have x1, the first vector, equal to here alpha n 1 2. Okay, and here the second one equal to alpha into 2 negative 1. Okay, so just clear and move to another example with the same sequence of steps. The eigenvalues and eigenvectors of the matrix A equal to 1, 2, 3, 0, 1, 0, 2, 1, 2. Okay, so here, first step is to get the determinant of the system A minus lambda I. So here we have this determinant 1 minus lambda 2, 3, 0, 1 minus lambda 0, 2, 1, 2 minus lambda. This will be equal to, let's go along this column. Okay, so we have here 1 minus lambda and 2 its value of its minor. So we have here 1 minus lambda into 2 minus lambda, and here we have 0, here we have 2 plus 2 into value of x minor. We have here into minus 3, here 1 minus lambda. Okay, here this will be equal to 1 minus lambda into 2 minus 3 lambda plus lambda square, here minus x plus x lambda, here this will be equal to 2 minus 3 lambda plus lambda square, and here minus 2 lambda plus 3 lambda square, here minus cubic of lambda minus 6 plus 6 lambda. This will be equal to negative cube of lambda plus 4 lambda square plus lambda minus 4 equal to 0. Okay, so from here let's factorize this. Will be laid to, here we have 3 bracket lambda minus 4 lambda minus 1 lambda plus 1. Okay, so lambda here, or the spectrum of A, will be a set of 4, 1, negative 1. Okay, so to the next step, to get eigenvectors by using Gauss Jordan. Here we have to solve the system of A minus lambda I into x equal to 0 using Gauss Jordan method. Okay, so here we have first one for x1. Here we have f lambda equal to 4. So this matrix will be equal to 1 minus 4 negative 3 here 2 3 here 0 1 minus 4 negative 3 0 2 1 2 negative 2 minus 4 we have here negative 2. Okay, so into x1 x2 x3 element of vector x equal to 0. Let's here augment three terms here 0 0 0 with our matrix. We have here negative 3 2 3 0 negative 3 0 and here 2 1 negative 2. Okay, so just first operation is to here divide first row by negative 3. Okay, here multiply first row by negative 2, then add to third row. Okay, so this will be equal to here 0 0 0 here divided by negative 3, so we have here 1 here negative 2 thirds here negative 1 0 negative 3 0 and here we have negative 2 into 1, then add 2 we have here 0 negative 2 into negative 2 thirds, so we have here 4 thirds plus 1, so here we have 1 4 thirds here negative 2 into negative 1 here minus 2 we have here 0. Okay, again with second row, so we have here to divide R2 by negative 3 to make the central element equal to 1, and here multiply second row by 2 thirds, then add to first row, multiply here 7 by 3 into R2, then add to R3. Okay, so this will be equal to 0 0 0. Here we have 1 0 0, and here divide on negative 3 we have here 1 0, and here multiplied by here negative 1 here 0 multiplied by 2 thirds, then add to first row, this will be 0 multiplied by 7 thirds, then add to third row we have here 0. Okay, so this will lead to, let me write this here, x1 minus x3 equal to 0, x2 equal to 0. Okay, So for lambda equal to 4, we have here x1 minus x3 equal to 0, and here x2 equal to 0. From here, I can say that x1 equal to x3, let x3 equal to alpha, then x1 equal to alpha. So here the first eigenvector is, we have here alpha 0. Alpha here is arbitrary value, here alpha into 1, 0, 1. Okay, so this is the first eigenvector related to this eigenvalue. Okay, again with lambda equal to 1. Okay, so matrix will be equal to 0, 2, 3, 0, 0, 0, and here we have 2, 1, 1, this into x1, x2, x3 of the second eigenvector x2. We have here 0, 0, 0. Okay, so using here eigen expression here, just to replace the first column by third one. So we have here, okay, 2, 1, 1, and here 0, 2, 3, and here we can use this, here x3, and here x1. Nothing will change. Okay, so here the next one is to replace second again by third. So you will have here 0, 2, 3, and here 0, 0, 0. Okay, and here we have x1, x2. Okay, so just arrange in augmented matrix. So here 2, 1, 1, 0, 0, 2, 3, 0. Here 0, 0, 0, 0. Okay, here the next operation is to divide first row by 2. Okay, so we will obtain, let me make this here 1, 1 half, 1 half. Okay, again divide second row by 2. So we will have here just 1, and here 3 half. Okay, here multiply second row by negative 1 half, then add to first row. Okay, so here we will obtain that 0, 0, 0, here 1, 0, 0, here we have 1 3 half, and here we will obtain 0. 3 half into negative 1 half plus here 1 half, so we'll obtain here negative quarter, and here 0 0. Okay, let me write that here. X3 minus quarter of x2 will be 0, and here x1 plus 3 half x2 will be 0. So f lambda equal to 1, we have here let x2 equal to 4 alpha, and alpha is arbitrary value, so the eigenvector x2 will be equal to, here we have x3 will be equal to alpha, and here x1 will be equal to negative alpha. So here we have alpha here, negative 6 alpha here, 4 alpha. Okay, so this will be equal to alpha into 1 negative 6 4. Okay, just clear and move to the last one. F here lambda equal to negative 1, so matrix will be equal to here negative 1, so we have here 2 2 3, here 0 2 0, and here 2 1 3. Let's augment our matrix. We have here 2 0 2 2 2 1 3 0 3, and here we have 0 0 0. The first operation is to divide first row by 2. Okay, so we have here 1 1 3 half. Next one is to multiply first row by negative 2, then add to third row. This equal to here 1 1 3 half 0, here 0 2 0 0, and here 1 into negative 2 plus 2, we have here 0. 1 into negative 2 plus 1, we have here negative 1. 3 half into negative 2 here plus 3, we have here 0, and here 0. Okay, again we just here divide second row by 2. Okay, multiply here second row by negative 1, then add 2 first row. Here add second row, so third row. This will be equal to, here we have 0, 1, 0, 0, here 1, 0, multiplied 1 by negative 1, then add to 1, we have here 0, we have 0, and here we have 0, 0, 0, okay? So from here, let me write this. Here x1 plus 3 half x3 equal to 0, x2 equal to 0, okay? So let x3 equal to negative 2 alpha, then x1 will be equal to 3 alpha, okay? So we have here, let me write the last solution here at lambda equal to 4, then x1 equal to alpha into here 1, 0, 1, f lambda equal to 1, then x2 equal to alpha into 1, negative 6, 4, f lambda equal to negative 1, then x3 equal to alpha into 3, 0, 1. Okay, I hope this is clear. And let's move to another one. Example, find the eigenvalues and eigenvectors of the matrix A. Okay, so let's start with our steps of solution here. Step 1 is to here get the determinant of A minus lambda I. Okay, so we have here this determinant of negative 2 minus lambda 2 negative 3 here 2 1 minus lambda, and here negative 6, here negative 1 negative 2 negative lambda. Okay, this will be equal to here negative 2 minus lambda into here negative lambda into 1 minus lambda, here minus 12 minus 2 into minus 2 lambda, here minus 6, okay, here minus 3 into negative 4 plus 1 minus lambda. Okay, so this will be lead to negative cube lambda minus lambda square plus 21 lambda plus 45 equal to 0. From here lambda will be equal to here 5 negative 3 negative 3, So here we have a new thing which called multi eigenvalues. Okay, so let's know how to deal with this. So just we will clear and start with second step is to find solution of system A minus lambda I into vector x. Okay, here we have f lambda equal to 5. Then here our system as this x1, x2, x3 equal to 0, and here we have -2 minus 5, so we have here -7, here 2, -3, 2, -4, -6, -1, -2, and here -5. Okay, so using Gauss Jordan method, so let's augment here three terms of 0, 0, 0, and here our matrix A minus lambda I, okay, to -3, to -4, -6, -1, -2, -5. Okay, this will make row operations. Okay, and this will be lead to vector x1 equal to alpha into this vector 1, 2, -1. Okay, again with here lambda equal to -3, so our system here equal to x1, x2, x3 equal to 0. Here we have -2 plus 3, we have here 1, 2, -3, 2, and here we have 4, here -6, here -1, -2, here 3. Okay, let's augment our here matrices. We have here 1, 2, -1, 2, 4, -2. Here, first row by -2, then add 2, second row, and here add first row to third row to make these elements equal to 0. Okay, so here we will have plus here 0, 0, 0, 1, 2, -3. Here multiplied 1 by -2, then add 2, 2, we have here 0. multiply 2 by negative 2, then add to 4, we have here 0. Multiply negative 3 by negative 2, then add to negative 6. So we have here 0. Here add here first row to third row. So we have here 0, 0, and 0. Okay. So the rank of this matrix is equal to 1. Okay. Number of non-zero rows. Okay. So here we have x1 plus 2x2 minus 3x3 equal to 0. Here, let me take x2 equal to negative alpha and x3 equal to here gamma. Okay, so let me rewrite the final result. F F gamma equal to 5, then x1 will be equal to alpha into 1 to negative 1. F lambda equal to negative 3. Then we have here x equal to from here x1 equal to 2 alpha plus 3 gamma. Here we have x2 equal to negative alpha gamma, x3 equal to gamma. So this will be equal to, here we have alpha, here 2 negative 1 0 plus gamma 3 0 1. Okay, so from this multi value we get two eigenvector as we see. I hope this clear. The topic of eigenvalues and eigenvector is very important, and to understand this will help us in both to make mathematical model or physical model. Okay, so I hope all of that clear, and thank you.